Okay, so in this lecture I'm just going to be doing a circuit problem. It's only one problem, but it has an A and B part. So that problem is, at the terminals of a element, the expression for current and voltage is I of t equals 20 e to the negative 5,000 t amps. V of t equals 10 times e to the negative 5,000 t kilovolts. And so we have our illustration here with I going into the terminal here, and we have our voltage drop across that element there. Okay, so the part A is to calculate the power supplied to the element at 100 microseconds. And then the part B is to calculate the total energy delivered to the element. So taking a look at the plot for the current, this is what that current plot is going to look like. So it starts off at 20, and then by the time it gets to 1 millisecond, it has decayed to approximately 0. Next, let's take a look at the voltage plot. That starts off at 10K, and by the time it gets to 1 millisecond, it also has decayed to approximately 0. So for the A part, the expression for power is P of t equals I of t times V of t. P of t equals 20 e to the negative 5,000 t times 10 e to the negative 5,000 t k. And so we end up with P of t equals 200k e to the negative 10 kt watts. That's our expression for power. And what we're going to do now is we are going to evaluate that power expression at 100 microseconds. And then when we do that, we end up with 200k e to the negative 10k times 100 micro. All of that, of course, is the expression for watts. Then next we have P of 100 microseconds equals approximately 73.58 kilowatts. So let's take a look at a power graph next. And that power graph, that power plot, looks like this. Starts off at 200k, and then it decays to approximately 0 watts. And at what we had here, 100 microseconds, what is that? 100 microseconds is going to be 0.1 milliseconds. So at 100 microseconds, what do we have here? Well, it's between 50k and 100k. So therefore, that makes good sense that our calculation here told us that we should be at 73.58k. And what do we have here? Between 50 and 100, that seems very reasonable according to our graphical plot that we have here. And so that makes good sense that we're at 73.58k. Okay, so next, our B part. From the definition of power, the energy is W of t equals the integral between 0 and t of P of alpha d alpha. And so now we have W of t equals that same integral of 200 e to the negative 10k alpha k d alpha. And so W of t now becomes equal to 200k divided by negative 10k. And all of that's being multiplied by e to the negative 10k alpha between the limits of t and 0. Then when we evaluate some more, we get W of t equals 200k divided by negative 10k. And that's being multiplied by e to the negative 10 kt minus e to the 0. And then now we have W of t equals 200k divided by negative 10k times e to the negative 10 kt minus 1. And then when we take the limit as t approaches infinity to get the total energy, that is, of Wt, we end up with negative 20 times 0 minus 1. And then ultimately that gives us 20 joules. So our final answer for B is 20 joules. So let's take a look at that graphic plot. And so the energy plot looks like this. And we have the energy going from starting from 0 terminating and converging to a value of 20 there across that same time span of 1 millisecond. So that is our final answer, 20 joules for that. So that is all that I have. That's all that I wanted to cover in this problem here. So thank you for watching. Hopefully it was helpful, and have a nice day.